Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. Resource abuse in AI systems refers to the exploitation of compute, storage, and networking capacity in ways that were not intended by system designers or that violate acceptable use policies. In practice, resource abuse covers a range of behaviors: unauthorized consumption of GPU or TPU cycles, repeated or wasteful queries that drive up billing, and patterns of interaction that intentionally or inadvertently degrade performance for others. The danger is twofold: immediate operational impact, slower responses, queued workloads, failed jobs, and hidden financial impact, surprising invoices, unplanned cloud spend. As you think about this risk, frame it both technically and economically. Abuse is not merely a systems problem to be rate-limited. It is a cost center and a business continuity concern. Effective defenses therefore combine engineering controls, economic levers, and policy. You must detect patterns that indicate abuse, quantify their financial effect, and tie automated mitigations to contractual or telemetry-driven thresholds, so short-term attacks do not translate into long-term budget shocks. Forms of cost abuse manifest in predictable operational behaviors that you can instrument and deter. Excessive API calls, whether from a misconfigured integration, a runaway script, or a coordinated bot network drive per request costs, and request queuing that harm legitimate users. Denial of wallet attacks intentionally force expensive computations, for example, issuing maximal length generations repeatedly to inflate billing. Inefficient prompt spamming exploits model temperature and decoding to force higher token counts for minimal semantic return, essentially turning a chat model into a token mining engine. Repeated retries, perhaps because a client misinterprets error codes, compound costs. When multiplied across thousands of sessions, they constitute a practical denial of service by cost. Your posture should therefore treat frequency, depth, and retry behavior as first-class signals, connecting them to policy actions, throttles, backoffs, or billing holds, rather than treating cost as an after-the-fact accounting surprise. Cloud resource exposure amplifies the problem because modern AI stacks leverage autoscaling and pay-as-you-go infrastructure. Mechanisms that are efficient in benign operation become levers for attackers when left uncontrolled. Autoscaling responds to demand spikes by provisioning GPUs and load-balanced instances, which is exactly what attackers exploit to drive cloud spend upward quickly. A short, intense burst of malicious traffic can translate into large bills by triggering rapid scale-ups. Shared environments increase blast radius. A single tenant or misbehaving job that hogs shared infrastructure can induce noisy neighbors and elevated tail latencies for otherwise well-behaved customers. Misconfigured alerts or absent budget caps turn ephemeral misuse into multi-day billing surprises that finance only notices after the invoice arrives. To manage these exposures, you need predictive scaling policies, budget-aware controls, and per-tenant isolation that prevents one actor's spike from automatically provisioning indefinite capacity at organizational expense. Prompt abuse scenarios show how cunning use of the model interface itself can be weaponized against cost and availability. Infinite loop prompting is a class of misuse, where prompts are structured to provoke the model into producing chains that effectively self-continue requests that cause the model to generate instructions that the client immediately resubmits, or that encourage multi-turn loops without human intervention consuming tokens and compute in a loop. Task chaining that is unnecessary or adversarial breaks single request semantics into many smaller, expensive calls, multiplying overhead compared to a single optimized prompt. Adversarial long context inputs intentionally pad prompts with irrelevant or dense content to push models toward maximal context window processing, thereby increasing decoding time and memory pressure. Token flooding deliberately, including high-entropy repetitive sequences, forces longer decodes and may break bandwidth or downstream storage assumptions. Defenses require both syntactic guards, limit context length, validate prompts, and behavioral thresholds, limit chaining depth, track recursive submission patterns, because the surface for prompt-based abuse sits at the intersection of client code, user intent, and model behavior. Training resource misuse is a high-impact variant of abuse because training workloads consume orders of magnitude more compute and can persist for days or weeks. Unauthorized job submission, where a bad actor gains access to a scheduler and runs expensive jobs, can hijack clusters, delay critical experiments, and inflate monthly cloud commitments. Hijacking GPU clusters for unrelated or malicious tasks such as crypto mining is an increasingly common threat in loosely governed environments. Attackers treat exposed scheduling APIs and weak tenant isolation as a cheap way to harvest compute. Privilege abuse in schedulers, improper role separation that lets a single account submit wide-scope jobs, magnifies this risk. The long lead times and complex resource graphs of training runs mean that automatic detection must spot anomalous job templates, atypical dataset access, or sudden surges in ephemeral container creation, and then quarantine or preempt runs before they burn out significant budgets. Governance here mixes access controls, quota enforcement, and billing attribution to make abuse both detectable and uneconomical. Inference resource misuse tends to be the most common and visible attack surface because it is externally exposed and often directly monetized. Mass automated queries bot farms issuing thousands or millions of prompts, both scrape model outputs and create sustained compute load that raises operating expenses. Brute force model probing, in which adversaries systematically explore input spaces to perform extraction or to map model behavior, requires issuing many focused queries that, while individually cheap, aggregate into substantial cost and intellectual property risk. Hidden scraping clients polling for output continuations or programmatic content dumps harvests, valued disproportionately to what legitimate usage patterns would dictate. Saturation of endpoints through coordinated low and slow queries or bursts can degrade quality of service for paying customers. Your defense blend must include per-key quotas, per-session budgets, adaptive throttling, and economic disincentives that make large-scale misuse an unattractive business proposition relative to its return on investment for attackers. Abuse detection metrics are the quantitative lenses that let you decide whether your prevention program is working, and choosing the right ones forces clarity about trade-offs between security and user experience. False positives, legitimate users blocked or throttled, represent an erosion of trust and must be measured as a rate and as a business cost. How many help desk tickets, lost conversions, or frustrated partners result from overzealous rules? False negatives, abusive sessions that slip through, are the direct harm you try to minimize and must be weighted by severity rather than counted equally with nuisance cases. Time to detection matters. The sooner you detect scripted scraping, token mining, or extraction probing, the less compute and fewer invoices you waste. Measure mean time to detect and mean time to contain. Monetary loss prevention is concrete. Estimate prevented chargebacks, avoided cloud spend, or saved incident response costs attributed to successful interventions. Finally, trust score accuracy for accounts and sessions. How well composite signals predict actual abuse ties detectors to operational decisions. High-quality scoring reduces human load and focuses remediation where it materially matters. These metrics together form the dashboard you present to finance, security, and product leadership, so investments in detectors are accountable and prioritized. Automated response measures turn detection signals into immediate, low-latency defenses that blunt abuse before it compounds, but they must be designed with graduated severity and explicit rollback paths. At the lightest end are output suppression strategies. When a generator or validator flags risky content, the system returns a sanitized or redacted response or an abstention message instead of allowing propagation to recipients. This prevents downstream exploitation while preserving session continuity. Next are throttles and soft caps that reduce throughput for suspicious keys or session slowing rather than severing access so legitimate heavy users tolerate brief friction. Stronger automated steps include temporary account suspension or credential revocation when high-confidence abuse patterns appear, and network-level actions such as blocking IP ranges or API key blacklisting for confirmed abuse campaigns. Critical is escalation to human review for edge cases. Automated systems should hand a concise evidence packet to analysts rather than leaving opaque flags. Each automated action should be accompanied by user-facing remediation paths, appeals, re-authentication steps, and clear explanations, so you limit collateral damage while staying decisive against attackers. Challenges in detection are systemic and often social. Technology alone cannot close the gap between clever adversaries and imperfect observability. Adversaries adapt. Once you block a template or token pattern, attackers paraphrase, break payloads into multi-step chains, switch modalities, or distribute queries across many low-volume accounts to stay below thresholds. Low-signal, high-noise environments make detection intrinsically hard. Legitimate partners or power users can resemble scripted patterns, while real attacks may simulate normal usage to avoid heuristics. Balancing user experience with protection creates governance tension. Overly aggressive thresholds reduce fraud but alienate paying customers, while permissive rules invite abuse. Data quality and instrumentation gaps amplify these problems. Missing correlation IDs, inconsistent schemas, or unlinked telemetry fragments prevent you from connecting suspicious outputs to accountable identities. Finally, human capacity is finite. Flooded queues from noisy detectors create alert fatigue and erode analyst effectiveness, so detection programs must be tuned to the organization's operational budget and adjudication throughput. Practical tools for abuse prevention form a layered stack that enforces policy as close to the ingress point as possible while supplying rich signals downstream. API gateways are the natural first barrier. They enforce quotas, validate token scopes, and apply simple syntactic checks to block malformed or obviously abusive requests at the edge. Usage monitoring systems continually aggregate call rates, per-key token consumption, and compute cost distributions so you can detect anomalies and apply soft or hard caps. Content moderation platforms handle fast, explainable checks, blacklists, regular expression-based filters, and lightweight classifiers that catch high-precision abuse with low latency. Anomaly detection services consume aggregated usage metrics and session characteristics to surface coordinated campaigns that single request rules miss. They often combine unsupervised profiles with supervised fraud models. Finally, human moderation tooling closes the loop. Triage queues, rich evidence packets, and rapid remediation interfaces let analysts confirm, annotate, and tune detectors. Choose tools that emit structured telemetry, integrate into CI/CD for policy deployment, and support safe rollbacks to avoid creating brittle, opaque rule sets. Tooling for fraud prevention extends beyond content filtering into provenance, identity, and transaction analytics because fraud converts content into real-world loss. Anti-deepfake models analyze multimedia artifacts for synthesis artifacts and mismatches, while watermarking schemes offer provenance tracing where supported by vendors. Identity verification APIs provide document checks, liveness detection, and cross-checks against authoritative registries to break synthetic identity flows. These are essential when onboarding new accounts that could be used for large-scale abuse. Transaction monitoring systems apply rules and machine-learned scoring to financial and credential change flows, looking for rapid beneficiary churn, unusual routing, or patterns typical of laundering. Fraud intelligence feeds and shared blacklists enrich signals with external context-known compromised keys, flagged wallets, or previously abused IP ranges. Together, these tools allow you to escalate from a content warning to a business action, hold a payment, freeze an account, or involve law enforcement when threshold conditions align with legal and contractual obligations. Integration with society processes turns detection outputs into coordinated organizational action rather than isolated alerts. Feed prioritized abuse and fraud signals into the SIEM enriched with correlation IDs, model version metadata, and the specific validator or detector that triggered the event so analysts have immediate context for triage. Align alert taxonomies and playbooks so society analysts execute consistent containment, steps temporary credential revocation, evidence preservation, and escalation to compliance without ad hoc decision-making in the heat of incident response. Use red team replay validation to ensure that society rules would have detected known adversarial patterns, and to populate detection models with labeled, realistic examples. Establish forensic pipelines that preserve immutable artifacts needed for legal processes, hashed prompts, signed ingestion manifests, and chain of custody logs, and automate the handoff to incident response and legal teams. When SOCs treat AI-driven abuse as first-class telemetry and not exotic anomalies, response times shrink and containment becomes more reliable. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Isolation of tenants is a practical defense against cost abuse because it prevents one tenant's spikes from automatically inflating another tenant's bill or degrading shared capacity. Per-tenant quota enforcement, both soft and hard limits, ensures that resource consumption is attributable and bounded. When a tenant approaches their budgeted threshold, automated throttles, warnings, or temporary degradations preserve node health while signaling the need for action. Separation can be logical namespaces, per-tenant indexes, distinct rate-limiting keys, or physical separate clusters, or reserved capacity for high-value customers, and each approach has trade-offs in cost and manageability. Cryptographic separation, such as tenant-specific encryption keys for stored artifacts and tenant-scoped API tokens, reduces cross-tenant leakage risk during forensics. Operationally, strict isolation simplifies financial attribution and forensics. You can trace a spike to a tenant, a job, or a user, and perform cost recovery or mitigation without broad collateral impact. Design isolation with elasticity in mind so you avoid brittle partitioning that prevents legitimate cross-tenant optimization while still limiting blast radius when abuse occurs. Secure autoscaling practices are a nuanced balance between responsiveness to legitimate demand and protection against flash-driven cost abuse. Predictive scaling that uses historical traffic patterns and business calendars can pre-warm capacity for known peaks and avoid over-provisioning during ephemeral surges that might be malicious. Controlled elasticity introduces budget limits and scale caps, so auto-scaling respects finance constraints. Beyond a defined cost threshold, new instance launches are either slowed or require human approval, preventing a short attack burst from producing a runaway invoice. Implementing cooldown intervals, surge pricing signals, and throttled pre-provisioning prevents immediate scale-ups on transient load spikes while maintaining user experience. Use capacity queues and graceful degradation strategies, such as returning lighter-weight model variants or cached responses, so service quality degrades predictably rather than failing catastrophically. Combine autoscaling guardrails with observability that surfaces anomalous scale triggers in real time, enabling immediate investigation and rollback if the scaling event appears abusive or accidental. Mitigation in APIs starts at the design level. Provide per-key quota keys, parameterized cost budgets, and revocation processes that are fast, auditable, and reversible. Enforce quotas at multiple layers edge gateways for quick decisions, mid-tier policy enforcers for contextual checks, and back-end metering for precise billing reconciliation, to ensure that a single bypass does not defeat all controls. Throttling should be adaptive. Gradual back-off mechanisms prevent sudden cutoff that frustrates legitimate users while making abuse expensive. Token bucket implementations with weighted priorities let critical, validated clients retain service while suspicious clients slow. Separate test and production environments to avoid accidental expenditure from experimentation and require explicit opt-in for high-cost endpoints or model variants. Implement schema validation and input size checks at the gateway to prevent adversarial long context inputs from reaching the model unnecessarily and make operations idempotent where possible to reduce the cost of retries. Finally, document revocation and appeal pathways so clients understand how to recover if their usage is mistakenly limited, and so finance and security teams can collaborate on chargeback or remediation when abuse is confirmed. Limits of preventative controls are a tension every organization must accept and manage. Many legitimate workloads are legitimately high volume, and aggressive throttles or quotas create false positives that alienate customers. High-performance analytics, real-time bidding, or large-scale batch inference may legitimately approach or exceed typical per-key thresholds, so detection logic must incorporate contexts such as verified account status, contractual SLAs, and pre-declared high-throughput tasks. False positive throttling creates friction costs, support load, lost transactions, and reputational harm that can outweigh the direct monetary savings from blocking some abuse, so calibrate conservative fallbacks and human-in-the-loop adjudication for contested cases. Provide explicit escalation and just-in-time quota increase mechanisms for validated users while maintaining rapid automated defenses for anonymous or unverified flows. Communicate transparently with customers about limits, alert thresholds, and remediation options so when protective actions occur, they are understood rather than perceived as arbitrary, which preserves trust even when enforcement is necessary. Integration with security operations centers and finance teams turns detection into coordinated response and recovery rather than isolated alarms. Feed abuse detection alerts into CEMs, enriched with billing metadata per key cost, projected spend trajectory, and historical consumption patterns, so analysts can prioritize incidents that threaten immediate financial exposure. Define incident playbooks that include forensic billing analysis, capture cost attribution snapshots, instance launch timelines, and autoscaling events so you can reconstruct how an attack translated into spend. Coordinate with billing and legal to enable measures such as temporary holds, contractual remediation, or retroactive chargebacks where contracts permit. Ensure playbooks specify communication protocols for customers affected by mitigation actions and include templates for disclosure when large billing anomalies require external notification. By linking security telemetry to financial controls and society processes, you institutionalize a fast, defensible path from detection to mitigation to accountability that preserves both operational continuity and fiscal prudence. Strategic alignment elevates cost and resource abuse controls from an operational nuisance to a board-level concern by tying detection and mitigation to business outcomes. Treat prevention mechanisms not as purely technical knobs but as financial controls. Integrate usage thresholds with budget approvals, map spike events to chargeback processes, and make anomaly trends visible to finance and product leadership alongside security dashboards. This alignment helps prioritize engineering work. If a connector routinely drives the worst cost spikes, product teams can justify redesign or price adjustments with quantifiable impact. It also clarifies risk appetite. Leadership can choose to accept short bursts of expensive load for business-critical flows while insisting on strict limits for open access APIs. A cross-functional policy, where security, finance, and product own thresholds and exception flows together, reduces surprise invoices and ensures mitigation decisions balance customer experience with fiscal prudence. In short, cost abuse defense becomes a shared control that preserves both technical stability and economic predictability. Operationalizing controls requires clear processes and playbooks so that detection translates into swift, consistent action rather than ad hoc responses. Define automated escalation paths. What triggers an immediate throttle, when an account is suspended pending review, and when a finance hold is applied to a tenant. Document remediation steps for engineers, how to quarantine suspect jobs, rotate compromised keys, and roll back autoscaling decisions. And for customer-facing teams, how to notify customers, offer appeal or verification channels, and process chargebacks or credits when warranted. Train teams with tabletop exercises that simulate cost abuse, a sudden extraction campaign, a misconfigured integration that starts spraying long context prompts, or a compromised service account firing costly training jobs. These rehearsals reveal gaps in tooling and decision latency and build muscle memory so real incidents are contained quickly. Well-drilled processes reduce both financial and reputational fallout by turning surprise into predictable, governed recovery. Design choices about pricing and product tiers materially influence abuse incentives, so economic levers should complement technical defenses. Consider tiered pricing that embeds natural throttles. Higher volume, high-cost endpoints require premium subscriptions or stricter vetting, so attackers must pay more to scale abuse and legitimate heavy users self-select into appropriate contracts. Offer dedicated capacity or reserved instances for enterprise customers who need high throughput, isolating their consumption from communal pools and making billing transparent. Use economic nudges like metered pricing for particularly expensive model variants to discourage gratuitous maximal length generations. When cost structures are visible and predictable to customers, they help surface misconfigurations early. Customers notice rising bills and report them, and shift some responsibility for efficient usage onto the consumer. Designing pricing and service tiers with abuse economics in mind reduces the attractiveness and feasibility of large-scale abuse campaigns. Technology investments that make prevention effective at scale include quota management platforms, fast edge enforcement, and integrated billing telemetry that ties usage to cost in near real time. Deploy per-key metering with enforced soft and hard caps that are configurable by customer tier. Implement edge layer checks to reject oversized prompts before they incur decoding cost, and route high-risk traffic through cheaper or degraded models automatically rather than letting it hit premium GPUs. Invest in relational attribution systems that connect an API key to organizational billing entities, so when abuse occurs, you can rapidly identify responsible parties and take targeted action. Link billing systems into alerting so finance teams receive early warnings of anomalous spend growth and can proactively engage customers, avoiding escalation to collections or public disputes. These technical building blocks make mitigation fast, precise, and financially accountable rather than blunt and disruptive. Accept that residual risk and trade-offs will persist. Plan governance to record, review, and iterate on incidents so the program matures rather than oscillates. Maintain a risk register that tracks recurring abuse patterns, their mitigations, economic impact, and residual exposure. Review it in cross-functional risk committees quarterly to allocate budget and prioritize engineering work. Preserve forensic artifacts time series of instance launches, correlation IDs, and snapshots of autoscaling decisions, so post-incident analysis can both allocate financial responsibility and feed improvements back into detection models and autoscaling policies. Regularly revisit thresholds and quotas as product usage evolves. What was once an anomaly may become normal as a feature scales, and your controls must adapt to avoid undue friction. By treating cost abuse controls as evolving governance artifacts rather than fixed rules, you keep defenses aligned with both technological change and commercial realities. In closing, defending against cost and resource abuse combines technical craftsmanship, economic design, and organizational governance. We reviewed the nature of resource abuse, how excessive API calls, prompt manipulation, and malicious training jobs translate into operational and billing harm, and explored control families, monitoring and attribution, quota and throttling strategies, autoscaling guardrails, tenant isolation, and billing integrated incident response. Success means more than preventing a few attacks. It means predictable cost patterns, preserved availability for legitimate users, and clear accountability when abuse occurs. As you implement these practices, prepare to integrate them with MLOps and serving security, pipeline-level safeguards, CI/CD gates that enforce cost-aware configuration, and serving layered defenses that reduce exposure to runaway workloads. This completes our episode on cost and resource abuse and sets the stage for the next topic: securing model deployment and operational MLOps to ensure models are served safely, efficiently, and sustainably. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.